On behalf of President Milstein and the General Committee, I now call to order the 2,386th meeting of the Society in the 146th year since its founding in 1871. Good evening. My name is Robin Taylor, and I'm the corresponding secretary of the Society. We welcome our members and guests to tonight's lecture in the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C. We also welcome our friends around the world who are watching the live stream of tonight's meeting on PSW Science's YouTube channel. You can follow us on that channel, on our website, on Facebook, on Twitter, and on Meetup. Our speaker this evening is Byron Cook of Amazon Web Services and University College London. His lecture is entitled, Automatically Proving That Computer Programs Do What They Are Supposed to Do. Please join me in thanking the sponsors of the 2017-2018 lecture series, the Policy Studies Organization in cooperation with the American Public University, and a generous sponsor who wishes to remain anonymous. Please join me in thanking them. In accordance with the tradition of the Society, I am pleased to announce that the following new members have been elected to membership. Alexander Mole, a management consultant with Accenture, interested in management science, crowdsourcing, and medicine. Matt Lesko, a software engineer with Palantir, with broad interests in science. And tonight's speaker, Byron Cook, whose interest will be obvious from tonight's proceedings. Please welcome them to the Society. Our last item of business before turning to tonight's lecture is the reading of the minutes of the previous meeting. I now call upon the Society's recording secretary, James Heelan.
President Larry Milstein called the 2,381st meeting of the Society to order at 8:04 p.m. President Milstein announced the order of business, announced the evening's lecture would be live streamed on the internet, and welcomed new members. The minutes of the previous meeting were read and approved. President Milstein then introduced the speaker for the evening, Antti Pulkkinen, Acting Deputy Director of the Heliophysics Science Division, NASA Goddard Space Flight Center. His lecture was titled, Space Weather, Earthly Effects. Dr. Pulkkinen began by explaining that space weather refers to the conditions on the sun and in the interplanetary space, which can affect human infrastructure both in space and on Earth. Space weather in our solar system is driven by the sun, and the science of space weather is plasma physics. Summarizing the fundamentals, Pulkkinen explained that because plasma is electrically charged, electromagnetism plays a fundamental role in dictating how plasma evolves. For example, the aurora borealis is a plasma organized along the Earth's electromagnetic field. Moreover, the temporal range of space weather scales is challenging, ranging from 10 to the minus 9 seconds to 10 to the 8 seconds, which is approximately 11 years. Similarly, the relevant spatial scales vary from 1 meter to 10 to the 8 meters, the size of our solar system. These characteristics make forecasting space weather a serious challenge. Space weather forecasting focuses on the 6600 Kelvin convection zone of the sun, which sits just below the cooler photosphere and is where plasma is most active. The motion of plasma within the sun is organized by the sun's magnetosphere. Clumping of strong magnetic fields results in sunspots, dark areas in the photosphere that are 1,000 to 2,000 degrees Kelvin cooler than the surrounding plasma. Reviewing approximately 400 years of sunspot observations reveals that the number of sunspots peaks approximately every 11 years. Large numbers of sunspots indicate additional complexity in the sun's magnetic field, which translate to an increased probability of major eruptions at the sun's surface. Those major eruptions include solar flares and coronal mass ejections. Lasting 1 to 60 minutes, a solar flare can release upwards of 10 to the 25 joules, mostly in the form of electromagnetic radiation, which exceeds the average annual world energy consumption of around 10 to the 20 joules. Coronal mass ejections release similar quantities of energy, but the majority of the energy released in a coronal mass ejection is released in the bulk motion of plasma into the surrounding heliosphere at rates in excess of 3,000 kilometers per second. While Earth's magnetic field largely shields us from charged particles coming from the sun, some charged particles do make it through. Mass energy creates electric currents that flow through the Earth's magnetosphere, generating magnetic field perturbations on the surface of the Earth. These fluctuations are called geomagnetic storms. While scientists have been interested in space weather since the dawn of the space age, it is its effects on modern infrastructure that have drawn political attention. Hundreds of years ago, space weather impacts were largely limited to impressive visual displays, such as borealis near the North and South Poles. But now, space weather phenomena can influence global navigation systems, high-frequency signals, microelectronics in spacecraft, and can disrupt ground-based infrastructure, such as high-voltage power systems. As a public policy concern, Pulkkinen said space weather began to receive high-level US government interest in 2008, following a report on potential major impacts of space weather on the high-voltage electrical grid. Space weather policy is now of concern to the White House and to Congress, resulting in what Pulkkinen describes as the golden age of space weather attention from the federal government. Now, in addition to worrying about spikes in radiation levels for astronauts orbiting in space, we must address the vulnerability of ground-based systems to major space weather events. For example, coronal mass ejections may cause geomagnetic storms that create large variations of electric currents to the order of millions of amps, which are hazardous to long conductor systems such as railway systems, oil pipelines, and of course, high-voltage power transmission systems. Fluctuations in voltage in high-voltage power grids may damage transformers and collapse systems. Such a collapse occurred in Quebec in 1989. Pulkkinen concluded, "We are still learning about the causes and effects of space weather. We are just beginning to develop the mitigation tools that will be necessary to protect us from major space weather events, as protection of systems that are susceptible to such events are increasingly crucial to the functions of society." President Milstein then invited questions from the audience. One questioner asked about whether private utilities are taking the necessary steps to secure power systems from space weather events. Dr. Pulkkinen said most US utilities pay attention to NOAA space weather predictions and have taken effective mitigation measures per federal regulation. A livestream viewer asked, "Given the recent increase in satellite communication infrastructure development during the current calm in the solar cycle, whether we are headed for disaster as conditions deteriorate." Dr. Pulkkinen said that while NASA has a rigid design criteria for its craft to withstand major space weather events, he believes commercial operators may not be developing their systems to the same specifications. Educating operators is key, Pulkkinen said, to encourage them to implement the necessary mitigation measures. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. At 9:40 p.m., President Milstein adjourned the 2,381st meeting of the Society to the social hour. Temperature, 18°C. Weather, clear. In-person attendance, 87. Respectfully submitted, James Heelan.
Thank you, James. Are there any corrections to the minutes? If there are no corrections, the minutes are approved as read. I now call upon the Society's President and Program Director, Larry Milstein, who will introduce tonight's speaker.
Tonight's speaker is Byron Cook, and he is the Senior Principal at Amazon Web Services and Professor of Computer Sciences at University College London. He has had a long and very productive career in computer science. He worked at several other companies that I'm not going to name, but while he was there, he developed some very important tools for predicting how computer systems work and for preventing them from doing things that they're not supposed to do. And I think I'll let him explain the rest of that to you. Without further ado, let me welcome Byron to the podium.
Thanks for coming. It's quite an honor. Perfect. Let's get started. So this talk is in the topic of what we call formal verification. So the idea is that we want to view artifacts of interest as mathematical systems. So that can be software, hardware, biological systems, railway switching systems, aircraft, or mathematical systems, right? If you want to reason about mathematical systems. And we'd like to prove properties about those systems using techniques from logic, mathematical logic. And as an activity, this was something that was quite active in the 1970s, really died out in the 80s and 90s. There's been quite a renaissance since the beginning of 2000, and the activity is having tremendous impact now in this decade. So I was going to try and describe at a level that's appropriate for a general audience interested in science some level of the history of this area and at some level of detail what happened and how are we able to do things now and we couldn't do them before. So we'll begin 360 BC. So there are an infinite number of prime numbers, and no one has ever counted them all. We don't have enough time, right? But yet we know that there's an infinite number of primes. So how do we know that there's an infinite number of primes? Someone described to someone else in finite time and finite space. You know, a whiteboard is a finite space, or a chalkboard is a finite space. A piece of paper is a finite space. So we've reasoned in finite space and finite time about the infinite. Yeah? And to do so in a way that you're going to be able to convince all of your intelligent members of the scientific community that what you're saying is founded on truth, you're going to arrive at a system that's going to be isomorphic to logic, right? So we're going to ultimately devise a system where we establish the truths that we all hold to believe, like modus ponens, you know, or various concepts. What's the meaning of and? What's the meaning of or, etc.? What's the meaning of negation? And then we're going to begin to build arguments in that system and try and convince each other that things are true. And we're going to do it in a way that's repeatable, such that people can tell that story again and again, or we can write it down, etc. So that's kind of where we were from the, and by the way, I'm oversimplifying greatly, right? So there's, I was talking to someone in the drinks before this event. They had actually worked on computers before they were electronic computers, right? So it used to be that computers were people, and your job was a computer, and you computed things like navigational tables. And so what's happened in the 40s, 50s, 60s, and 70s is that electronic computers became a thing. So I'm marking 1970 as largely out of simplicity. So what I'm going to say is that from 360 BC until the 1970s, essentially reasoning happened. Here I've thrown up a couple examples: Gödel, Turing, Euclid. Essentially, reasoning happened by writing things on pen and paper, communicating things to your colleagues while you're writing on trains, that sort of activity. Journal papers and so on. And so there's two activities when you're doing proofs, and they're actually quite different. One is very creative and one is extremely boring, right? The creative activity is finding the proof, the beautiful mind moment, right? There's formulae everywhere, and you're creative and your hair is all messed up and so on, yeah? And then there's the re-explaining it over and over and over again amongst the community. You're maintaining, in some sense, an oral history of why things are true, right? And there's interesting papers like Turing proved something that wasn't quite proving someone asked me just before the talk about the halting problem. We'll be talking about the halting problem. But Turing proved something that wasn't quite the undecidability of the halting problem. But then there's an interesting paper by Strachey describing his train journey with Turing, where Turing described to him the proof of the halting problem. Then he produced a journal paper on that discussion about what they discussed in the train journey from Cambridge to Oxford. So there's the finding of the proof and there's the checking of the proof. And in the early days, they were done by humans, and they're really different. The finding, in some sense, the finding is the hard part, and the easier part is the double checking of the argument. And the double checking of the argument is on purpose supposed to be really boring. It's supposed to be repeatable. There should be no insight whatsoever. The entire point of proof is that you can develop a finite space, finite time argument that's repeatable by machines or by people that doesn't require any insight. Okay, I've said all that. So beginning around 2001, we began to see really interesting work where the four-color theorem is one of the most interesting ones, where the four-color theorem, so the four-color theorem, by the way, is that if you have I'm just going to describe it in layman's terms. If you have a map of the world, a two-dimensional map of the world, or Europe, or United States, maybe the counties in the United States, you'll never need more than 4 colors. Right? Because you can always, like for example, Ohio and New York State, you can use the same color. Florida and California, you can use the same color. You're never going to need more than 4 colors, and there's a theorem that you'll never need more than 4 colors. And the proof of the four-color theorem really couldn't be achieved because there's a massive combinational argument. There's a number, like so many cases to go through in the known proof that no human could do it. So what happened is that someone wrote some programs that rolled through all. So there was a bunch of intuitive, creative reasoning that happened, but then there was a bunch of reasoning that was encoded in a computer program. Oh, but the computer program wasn't quite correct, right? So like the computer, and then questions begin to arise about, wait, how do we know the program that did the reasoning is correct, and so on. So that's an issue, and so those things began to get worked out. So we begin to see proofs that are in systems that are correct, right? So you have Koch theorem prover, HOL theorem prover, Isabelle theorem prover. You have what they call mechanical theorem provers, where a human encodes a proof and the machine checks the proof. And the axioms encoded in the machine are simple enough that your colleagues can look at the axioms and decide that's right. And the trusted core is so simple that everyone believes the trusted core. And we assume that the underlying computer that we're using is correct, and that's something we'll need to talk about. But let's assume that that when you call the plus operation in a computer, that you get the right answer, which doesn't always hold, by the way. Floating point division bug in Intel microprocessors in the 1990s taught us that. But let's assume it's true. Then now you've built a proof, and you've convinced a mechanical theorem prover that the thing you're trying to hold is true. And this happened for so the odd order. So George Gontier proved four-color theorem and odd order theorem, and so on. And it's a common exercise to for example, prove the Turing's result. Now, I just want to remind you that we're heading into very dangerous territory here, right? So when you begin to use computers for these activities, because it turns out, and I'm going to go into a little bit of detail, and by the way, I'm going to lose some of you in this talk. You're not going to understand what I'm talking about, and that's part of the theater, right? That's why you're here, okay? My advisor taught me to make a third of the talk easily understood, a third of the talk hard to understand, but approachable by your specialist area, and then 1/3 of the talk I should just lose you, and that's the whole point. Because if I make it too easy, you're not going to think I'm smart. So that's what I'm going to do, okay? And so you're gonna lose track, but the talk is structured so that you can always jump on the next wave, right? We'll come back to an area where you can check in again. So formally speaking, these problems are either undecidable or intractable. And this is undecidable means there cannot exist a computer program that solves them. Or intractable means that the speed, that the performance of the procedure does not scale well with the size of the problem. And actually encryption is based on this concept. You encrypt messages using keys that actually computers can hack, but it would take many lifetimes to hack them. So by the time they actually discover the key, the secret doesn't matter anymore. So undecidable or intractable problems, that's what we're going to be talking about all night long. And so, so things get very tricky. Great. Oh, by the way, these same approaches you can use for artifacts, right? So helicopters, computers used in Mars rover, AMD square root microcode, the logical operations in the superscalar out-of-order microprocessor core, et cetera. So you have commercial artifacts where correctness matters, and if it matters enough, what you see is organizations begin to invest in using those same techniques, logic, that we proved about prime numbers to reason about these devices. And some of them are finite state, so it's decidable yet intractable. And some of them are like protocols. They're designed to work, and they're unbounded, right? You don't know how many, like the internet, you don't know how many devices there are going to be. So it's easier to think of them as unbounded. And you're doing reasoning in the same way you are about the integers, reals, rationals, whatever. Okay, now things get really interesting. So what I was describing to you before was this idea that we can ask a smart person to try and convince a mechanical theorem prover that a theorem holds, but actually you can write software to try and pretend they're the smart person, right? So there's two activities. There's discovering the proof, trying to discover the proof, and then there's the checking of the proof that has been found. And usually the checking of the proof that has been found is relatively easy. The discovery of the proof is typically undecidable, and so we have to use heuristics, and those heuristics may fail, and often many cases we'll fail to find a proof, but in some cases we can find a proof. And that's the activity we're describing. I'm gonna describe this area by choosing a couple of examples and describing them in some detail, but the same approaches apply in lots of domains. So for example, I've worked on Intel microprocessors, I've worked on aircraft software, I've worked on representations of nuclear power plants, I've worked on device drivers, which is I'm going to tell you a little bit about, and I've worked on models, biological models. So for example, leukemia, skin cancer, diabetes, C. elegans. And one thing I want to try and make clear is that I usually have no idea what these systems are, right? Like I'm not a I mean, I've worked with pharmaceutical researchers, and we build models, but then I'm reasoning about the models, and then I'm writing software to reason about the models. I don't understand, I really don't understand the first thing about leukemia, but I understand mathematics. Great. So, to answer someone in the audience who came up and almost looked panicked and said, but wait, how do you deal with the halting problem? So if you study computer science in university, the first theory course you take, they're going to explain to you something called the halting problem. And the halting problem is a very interesting problem. It's very easy to explain, and I actually can give you a taste of what the proof looks like. So I'm going to do that. I'm going to lose a few people, but try and hang in there, okay? And I'm going to show you a little bit of code, but I'm going to walk you through it and just explain what's going on. So here's the following problem. Can there exist a program, right? Maybe you buy a program, and this program, what it does is it takes another program and it answers a question about that program, right? And what the question it answers is there a way for that other program ever to get stuck in an infinite loop? So if you've used Windows, you'll have this hourglass symbol. It just hangs out there forever. If you use a Mac, you get that spinning beach ball, and it just hangs out there forever, and you don't. And eventually, you kill your computer, or based on the age of some people in the room, you call your son to kill your computer. And the question is, can I answer? So I want to build a system that answers questions about all the other systems of the world. You can take any system, pass it to this program I'm writing, and it will answer truthfully, yes or no, and it will always answer. So it will never say I don't know whether or not there exists an infinite loop in the program or not. That's called the halting problem. And that's actually Turing's, this is the word decision problem in German. And this was one of the first known problems that people realized that you couldn't use computers to solve everything, right? So if you think about this is in the 1920s and 30s, people were extremely excited about the idea of computers. They had just, the mechanical computers had just begun, and secretly in labs here in Washington area and in university, the halls sponsored by government, and in Bletchley Park in the UK, you had people building what became digital computers, and so people were like, wow, we can use computers to solve all the world's problems. And Gödel and Turing and some folks found some problems that you can't solve with computers. And the halting problem is one of them. And I'm gonna try and show you this is the paper, 1936 is when he produced this paper. This program, well, that got really loud suddenly. This program is a witness to the undecidability of the halting problem, okay? So we're gonna do a little proof, right? We're gonna do a little bit of reasoning. So we wanna prove that there cannot exist a program. So I'm going to say, let's assume that there is such a program. And then I'm gonna assume that there exists one. I'm going to use it a little bit, talk a little bit about it, and all of a sudden everything, yes means no, and upside down means the opposite. It's opposite day suddenly. And we're gonna realize that because the existence of the thing I said can't exist, because it exists, nothing is true anymore, and for that reason, the program can't exist, okay? So imagine that there exists such a program. I'm gonna call it P, okay? So get my pointer here. So P is the procedure that we're writing, and I've written a little bit of code, but I'll just walk you through it. Sorry, this should say, oh, yeah, that's fine. Let me try again. Halts is the program, that's the procedure that answers truthfully whether or not programs terminate or not, okay? And then P is a program I'm writing, okay? So the question, does P halt or not? Does P always return an answer, or could it get stuck in an infinite loop? The programmers in the room might look at it and try and decide, okay? Let's look at what this program does. Oh. It says, if the program P halts, then don't halt, because I'm actually calling P again, right? So there's this program P, and I'm asking, hey, do I halt? If I halt, then don't halt. So call myself again, and thus we're stuck in an infinite loop where it's going to keep calling itself recursively forever. And it's all because the procedure which says that it can answer questions about whether or not programs halt or not has said that the program halts. And if the procedure halts says that P doesn't halt, then I exit, i.e. I halt. Right? It's somewhat analogous to the statement, I am a liar. The problem is that the language is too powerful. It's able to describe itself, and you get twisted up. The barber of Seville who shaves all the men of the town who don't shave themselves. Does the barber of Seville shave himself or not? Right. So these kinds of questions, and that's how you get into trouble. And because this program leads us into trouble, we know that there can't exist a procedure called halts, which does what, as advertised before, that it returns true whenever P guarantees termination and otherwise returns false. So there, we did a little proof together. Hope that was interesting. But this has tremendous commercial application, right? Since there are so many biologists in the room, I've talked to some folks before. Cancer is non-termination, right? It's a bug. It's a termination bug in the genetic regulatory pathways in your cells, right? We'll talk a little bit more. I'll hint to some of that work. In computers, for example, this computer here, the mouse device driver event handling routine should always terminate. So when I move the mouse, the code in the computer that's handling that movement should do something and then always return control back to the computer. Otherwise, we're in trouble, and this computer is going to hang. And I have given this talk a few times in my life, and it's pretty remarkable how often my computer would hang during talks about this material. So we'll see if we get through that. So when we are trying to reason about device drivers, now here I'm going to show you a bit of code and you don't really need to understand. This is the sort of thing we're doing. We're looking at programs like this. This is a bit of code from Windows mouse device driver infrastructure. And so it's a for loop. So it's basically doing this, the body of the loop. So from, here, I will use here. I said I wasn't going to use it, but I lied. So it's doing this code over and over and over and over again until actually until entry is not equal to whatever this expression means. Okay, so when we're trying to prove termination of device drivers, we're taking source code like this, and we're trying to reason about, does there exist an infinite execution through this code? That's the challenge. And I will, so we know how to prove termination. Actually, so Turing proved the undecidability of the halting problem, but he also told us how to prove termination of programs. Kind of curious. So there was a paper called Checking a Large Routine. Here, I've grabbed a little snapshot of it. He says, so we're trying to prove termination. So the checker, the person, us, has to verify that the process comes to an end. Here, there are lots of women programmers, but anyways, he should be assisted by the programmer giving further definite assertion to be verified. This may take the form of a quantity, which is to be asserted to decrease continuously and vanish when the machine stops. And then this is the important point, and there's, understand that a lot of people with mathematics backgrounds, basically we're mapping program states to ordinals. So to the pure mathematician, it's natural to give an ordinal number. And so I'm going to describe this in a little bit of detail. So what is a program? A program is a set of states, set of configurations, and transitions between those states. So when I move the mouse, the program is going from a state where the mouse is on the top right to the bottom left, right? So we've transitioned from a state to another state, and I'll call that transition relation R. Pre-state, post-state. And then what programs are, in a sense, is the graph of all the possible states, all the possible reachable states. And often you'll have a program where from a state you could go left or you could go right. There's different possible states you could reach. And graphs for programs are typically unbounded or infinite. And to prove termination, what we're doing is we're trying to find a structure-preserving map from states to an ordinal or to well order. So imagine that the bubbles on the right are some well order. If you imagine, for example, the natural numbers, so 0, 1, 2, 3, 4, etc. And we're trying to find mappings from states over to the numbers, right? And so what Turing is telling us to do is he's saying find a mapping such that the following holds. Whenever it's possible for the program to take a transition from a state, if you use the mapping over to the numbers, greater than should hold between the numbers. And if you choose an appropriate domain, so it's like the integer, the natural numbers, so for example, there's nothing between 0 and 1, there's nothing between 2 and 1, and there's a least number, the least element, so 0, then the greater than is the right thing. So if you can find a mapping that for all states of the program, whenever you map over, greater than always holds after a transition, you've now proved the termination of the program. So that's the mathematical argument for termination. And I know there's some glazed eyes, but there's also some very excited computer scientists who know exactly what I'm saying, so that's fine. And we'll just use a little bit of mathematical notation. So we're saying that the transition relation, that's a set of states, is a subset of the mapping of the function, and then we're lifting the greater than relation. So here, and this is the only formula in the entire talk, we're saying that the lifting of greater than is the set of pairs of states S and T, such that when you map with F on S and T, greater than holds. So this is it's kind of an interesting relationship. It's a relationship between states in your program, saying, but with the mapping. Okay, I know I've lost a bunch of people, but it doesn't matter. So, so the difficulty in proving termination now is two things, kind of interesting. So we have to do two things. We have to find this mapping, And then we have to prove that this inclusion holds. If we've done that, we've proved termination. So termination is, does there exist a function such that this relation holds? And it's undecidable in theory, and it's hard in practice. If this talk were for a computer science audience, I would go into some detail about how that works, which I'm not going to do. But I'm just going to show you the slides really quickly so that the computer scientists in the room or the folks with a mathematical background can come chat with me, and we'll go through those slides. Okay, and we'll call that done. The other thing is finding the F, right? So we're saying we've proved the inclusion, and the question is, how do we find an F? And here I'm going to attempt to describe that in just a little bit of detail. So what I'm going to do is I'm going to relax a constraint. So I said to you that the halting problem was, can you in a finite amount of time with 100% accuracy be able to take any program in and answer the question, does the program terminate or not? I'm going to relax the constraint that we have to always answer in a finite amount of time. I might not terminate itself, right? The procedure that the termination prover, the procedure that's going to take programs in and reason about them, might just run forever. And the analogy I use that seems to resonate with people not in sciences, not in mathematics, is that airline travel is not safe. Do we agree with that? Have we flown? Yes, we have all flown. So it is unsafe, but we do it anyways. Why is that? When you fly, you know when you got there that you got there and you're safe, right? And the occurrence of crashes is so low that you feel comfortable with your chances. So by the same analogy, if we can make tools that might not give you an answer, but when they give you an answer, you know the answer is correct, and they give you an answer often enough that you feel comfortable spending time with it, then you have succeeded, and that's what we're doing. So I have not solved the halting problem. I remember one time so there's an article in, I did some work, and there was an article in Financial Times and all the newspapers, and I remember begging a reporter, please don't tell people I solved the halting problem. Please, just if there's one thing, don't tell people I solved the halting problem. If you look at the Financial Times article about the work, they say, and he solved the halting problem, and all 200 people from my community made fun of me. Yeah? So anyways, so this is a procedure that's going to, and this is a very important concept. It's called, in our field it's called, and I think this concept appears in every mature scientific discipline, so you're going to recognize it. We call it counterexample guided abstraction refinement. So the idea is we're going to reason about the infinite, but we're going to build a finite abstraction of the infinite, but the finite abstraction is going to lose a lot of information, so we're going to iteratively refine the abstraction. We're going to make the abstraction better and better and better until it's good enough to get what we need out of it. So what we're going to do is we're going to start with an empty termination argument. We will assume that we know how to check this inclusion, because I said we already know how to. We're going to ask, hey, does this inclusion hold? If it doesn't, we get a counterexample, and this is a path through the program. We're going to add that path to the set of paths that we're keeping around. And then we're going to ask, hey, is the path a real counterexample? Is this really a case of non-termination? And there are some ways of doing that. And if it is, then we report to the user, your program doesn't terminate. And if it isn't, then we're gonna refine the termination argument and put it in the termination argument, and we're gonna try again. And so this loop here might never terminate. But if it does, then we say you've terminated. That's the procedure. Yeah, I'm going to sort of walk through this a little bit. So we're going to check the inclusion. The inclusion never holds the first time. We get a counterexample. We analyze it. We learn, and we use some things. And that's a really neat thing. So all these techniques are based on Ramsey's theorem, Farkas lemma, all these results from like 1900s. We dig them out because during those times they were reasoning about infinite graphs. It's really fascinating. So Ramsey's theorem was describing, like for example, Ramsey's theorem says if you have an infinite graph with fully connected with finite colorings on all of the transitions between the nodes in the graph, there exists a infinite monochromatic path through the graph. So you can remove all the colorings but one. There will be an infinite path through the graph, the transitions, that only has one color. And that theorem turns out to be quite key to some techniques for how we prove termination, and also Farkas lemma. Anyways, so we refine via application of Farkas lemma, and we write some code that solves these problems. And I won't go into this, but the computer scientists in the room might ask, hey, how do you do that transition? This is it, but I'm not going to describe that here. Or this one, or the other one. It's interesting giving talks to different communities, because you're trying to appeal to the different audiences at different levels. Okay, great. So we wrote a paper about this work. We called the tool Terminator. Terminator took in C programs and attempted to prove termination of the C programs. We applied this to real device drivers. So at the time, this was 2006. So it turns out that if you are working at a company, say you're working at Fujitsu or working at Logitech, you're writing mics, you're writing keyboards, or you're developing cameras, or whatever the device is, whatever this is, you will end up writing device drivers that work for the Mac, that work for the Windows, that work for the Android phone, whatever. And typically how you're going to do that is you're going to go to a set of known sample device drivers written by the maker of Microsoft or Apple or whatever, and you're going to copy and paste them over. You're going to find the one that's closest to the one you're trying to write, and you're going to modify it, and you're going to get it to do the thing you want it to do. That's how people write device drivers. Right? It's actually how people write a lot of programs. And so we ran this analysis on the sample device drivers, and they were but they were real device drivers. So it was keyboard, mouse, SCSI, printers, serial port, all kinds of device drivers. There were 23 device drivers in that sample set. And you can see the number of, lines of code. So from 1,000 lines of code, 5,000 lines of code, 8,000 lines of code, up to 35,000 lines of code. And the thing is, these device drivers have to deal with a lot. They have to deal with plug and play. I don't know, this might not go very well, but here we go. So I've just unplugged and replugged in, right? And so the device driver is having to deal with that situation. And if you want to find a bug in a program, yeah, try this. You plug it in really fast over and over again. And often you can get the machine to crash. Oh, okay. Let me plug that back in. Hopefully your machine makes it. Sorry for the abuse. This is the number of loops. So there are 75 loops in this device driver. Right? There are 31 loops in the device driver. Sorry, this was written. This is just a screenshot from the paper. So, this is the number of bugs that we found, true bugs, real termination bugs, in those device drivers. Right? And this is the number of false bugs, i.e. the tool actually gave an... So the tool was sound, but sometimes reported bugs that weren't real. That's an issue there's a whole another talk about how to reason about programs that are interfacing with other programs that you don't have the code for those other programs. But anyways, that's a separate talk. So, so in cases where we see 0 and 0, we prove the termination of that device driver. So in these cases, we proved the termination of the device driver, and then here we found, so I think it's something like 5 or 6 real bugs. What's interesting about this is that, and by the way, this tool, I didn't tell you the details, but the part I totally skipped over where I said let's not discuss that, and I just skipped through the slides. That was based on work I had done previously that became a product called the Windows Static Driver Verifier. And then this stuff now is similarly used. Lost my point. Let's look at one of the bugs. Okay. So it's this loop, our old friend. We saw this before. So let me just describe in a little bit of high-level detail what's going on. So let me just read the program first to you. So for those of you who don't know C programming language, which I imagine quite a few of you, I'll just tell you what this is saying. It's like reading to my kids. So it's saying, hey, so it's do this over and over again. This is how you initialize. So there's a variable, it's called entry, and it starts here. And then while entry is not equal to this thing, do this on every iteration, and then do all of this. And so it's doing some stuff I don't know. Here's a kid that says, if this is true, then do these things. Else, nothing. And there's inside of this if, there's another if. So it's if this, then do this, else do this. And what this code is doing is it's actually operating over a data structure. So here I've drawn it. So there's a set of nodes, and typically these are like the events. So it turns out that when you move your mouse, that event is put into a queue, and then there's some other code that's coming along and taking items off that queue and then doing things with it, like having the effect. So this code is operating over this. So this queue, here's the head of the queue, and this is the next item in the queue, this is the next item in the queue, and et cetera. And it's actually cyclic. So you can get from the last item in the queue back to the first item in the queue. So we call it a cyclic list. And this is actually, you can go both ways. You can go from this list back, but I haven't really described that. So this code is walking over this structure, looking for an element, and it's going to try and remove the element. So here, entry, that variable entry, is, let's imagine it's pointing to this element here. So it's removing the entry. So we've just removed the entry, right? So what we did is we made the node before it point to the node ahead of it. So actually, this node still points into the list, but it's no longer a part of that list, because from the start, you can no longer find it, right? So if we walked that list, we'd never find the red node anymore. So it's actually been removed, okay? And by the way, kind of just a little heuristic, I've spent a lifetime now of looking at bugs in computer systems, and the bugs always are accompanied by lots of comments by programmers who are basically admitting they don't know what they're doing, right? So look at, the comments get very long, and they're in trouble, right? They're saying, I think that we're doing this, and it's very complicated, and often there's misspellings, and now you know you found a bug. So it turns out this expression and entry are the same, and this initialized list head, what this does is it creates a new list. So a new list makes itself point to itself, right? So I'm just going to execute that. So now entry points to itself. So this is now a list, and this is another list. So we now have two lists, right? And you can just see it in the picture. There's two cyclic lists up there. And entry, which is the one we're walking over, is the node, okay? So now this is meaningless, and what this is saying is, giving away the punchline. It's saying that this node, I should use the pointer. It's saying that we're going to keep executing this loop while this node doesn't equal this node. But notice we can't get from this node to this node anymore because we've lost that path. So actually, we're just going to keep executing this loop forever now because we made a separate list, and now we're walking this list forever, looking for this element. So now we're screwed, and you're going to get this spinning beach ball or whatever. Oh my God, yeah, I did it. Wow. So it is interesting because I often try that trick where I plug things in and out and so on. So are you going to be okay if I reboot it? Larry? Is this the actual driver? Oh, wait, maybe that'll help. No, because it's a different operating system. Oh, there we go. Okay, maybe we're in business now. Okay, good. So I asked my friend in the development team, is this a bug? And he says it is. This is a bug, in fact. And the amazing thing is you don't even get the courtesy crash, right? It doesn't even have the decency to leave. You know, it's like the worst, the house guest that will never leave, right? They're acting up and you can't get them to go. So this turns out to be a really interesting thing, because when Windows crashes or Apple Mac crashes or computer program crashes, in a way it's really good news, because now you can like look over you can get a crash dump and you can look over the information, figure out what happened. Like you can, but when the computer program runs forever, there's kind of really not very much. It's much trickier to figure out what's going on. Anyways, so we found a bunch of proofs. There's a bunch of cases where we don't know the answer, right? Because I said I'm in this new world, I'm free to say I don't know. So if we gave a false bug, but we don't know if the program terminates. So then we began writing papers that solved this different aspects of the problem. So here's pointers to different papers where we're chipping away at that question mark. So you know, in the original days to prove the termination of a device driver, it took 80 hours, and then we got it down to 8 minutes, and we get it down to 8 seconds, right? And then we have to deal with concurrency better, and we have to deal with nonlinear operations. So we could only handle linear, like programs with linear arithmetic, not nonlinear arithmetic. And so, you know, there's some device drivers never use nonlinear arithmetic, but some applications do. So we developed techniques for that. And there was an article in Scientific American about this work and about me, and that was my moment of fame, and continued on. Turns out if you're trying to reason, I'm just doing a little time check. How are we good for, yeah? Well, you don't know how long my talk's going. How long do I have?
15, 20
This talk might never end. I've got all the time in the world. So it turns out if you are trying to say, imagine you're trying to ask a question about a program, and you use the word eventually. Like, for example, when I press the button, do the rockets get launched eventually, right? When I hit the brakes, does the BMW actually stop, right? That kind of thing. Whenever you say eventually, you're actually talking about program termination. Because how you could get into a situation where you don't hit eventually is when you get stuck in an infinite loop right before the thing you're supposed to do. Right? So if you push the button and then there's some code between the event, the button press is received, and then the rockets are launched, and then there's some loop where it's like going over and analyzing a tree's data structure, and it gets stuck and it starts doing something forever, then the rockets won't eventually be launched, and so it violates the property. So it turns out whenever you're talking about programs and you're using the word eventually, you're talking about termination, and there's a logic for describing that. So this temporal logic formula, it's really interesting. So Amir Punelli, who died recently, he's a Turing Award winner, discovered that these temporal logics, these modal logics, which come from logic, were really useful for reasoning about programs that might run forever, right? Like this program, in theory, should be able to run forever, right? We don't want the operating system to terminate unless we choose to, but then you want the event handling routines to terminate. So to reason about programs that might run forever, you can use these modal temporal logics, and they're really useful. So here, let me read this to you in English. This is saying, is it always true that whenever x is 10, then in the future, x will be 20? So it's something like, is it always true that whenever I get, the value is press the button, then eventually the rockets are launched? Or whenever I acquire a lock, do I eventually release the lock? When I when I try and sell stock, does the stock sell happen? That's the kind of reasoning we're trying to do. And it turns out that if you have a termination prover, you can convert that to a question of termination. It's the same. They're equivalent in difficulty, and you can do a conversion of one problem to the other problem. And there are various ways of doing that. Yeah, I said that. So yeah, I mentioned this before. So you are a trying to answer questions about genetic regulatory pathways. So with colleagues, we developed a cloud-based system where you have cells and you have genes and you have connections between them, and we want to answer questions. The biologists have a name for it. I've now sort of paged that information out, but it's basically termination stabilization. They had some other name for it. I'm sure you know what it is. But essentially, when the system is perturbed, does it always go back to a stable state? That's the sort of key question that they're trying to answer. And there are, I have a Nature Scientific Reports paper about using this computation to try and reason about leukemia. And so there are folks using this tool for drugs, target search, and so on. Great. So let me just remind you, let me take you back to the beginning of the talk. So this area, we call it deductive verification, formal verification, automated reasoning. There's different names by it. We are trying to use the techniques from ancient logicians, ancient philosophers, to reason about typically industrial artifacts. That's who typically pays our bills. And those tend to be software, hardware, biological systems, various kinds of devices. The area was very exciting in the 60s and 70s when you had people first thinking maybe this is something we could do. And then we realized it was actually much trickier than we thought. And so the world became, the industry became very disillusioned, and you didn't see work in this kind of space at all. There are some innovations that happened. I happened to be involved in some of them, which brought the area back. So there's a lot of people, a lot of companies, a lot of tools, a lot of activity in the space nowadays. And I guess that the lesson learned, and maybe you've there's many distinguished scientists in the room, maybe you found the same to be true, that how you solve these kinds of problems is you don't sit hidden deeply away in the ivory tower trying to think deep thoughts with just you and your PhD students, never interacting with the world. What we found in the field is that it was actually much better to work directly with the customer in some sense, right? Directly with the cryptographers, the device driver writers, the pharmaceutical researchers, and we developed techniques that worked for niche areas, and then from there generalize those approaches. So now if we find a new area, we're like, oh, I'm like, hey, when I applied these techniques for biology and hardware at Intel, I found the such and such approach worked. I wonder if we couldn't cobble together something in a slightly different way and apply it to this new area, and that's sort of the state of the art in my field. So it's somewhat counterintuitive, because as scientists we're taught to ignore the stresses of the commercial marketplace, yet it's the stresses of the commercial marketplace that cause us to do good science. That's been my find. Is there some construction going on? Okay. So yeah, that concludes my talk. Thank you very much. I believe there's a microphone and a...
There will be. We do have some time for questions. So our procedure is as follows. If you would raise your hand if you have a question, and a runner will bring a microphone to you. When I recognize you, I'll call on you by name or by your microphone number. And then if you would stand, state your name, tell us whether you're a guest or a member of the society, and then so that everyone can hear you and so that your question can be accurately transcribed for the minutes and heard on the recording, just please make sure that your microphone is fairly close to your mouth when you're speaking. And so that we can get to as many questions as possible, we'd appreciate it if you would keep your question brief. And if you're watching on the live stream, just enter your question in the chat box. So shall we begin? And microphone there, right there, please.
Hi, Michael Clifford. How do you trade off between uncertainty? Test. Hello? Okay. Sorry.
Put the microphone near your mouth and keep it there.
So how do you trade off between your degree of uncertainty in your solution and your need to actually have an accurate solution?
So the tools that we build are, when they give you an answer, the answer. Well, there's techniques. So there's the technique that I describe to is to build tools that when they say the program is correct, the program is correct, and we find a proof in logic. So there's no uncertainty. The uncertainty is, well, actually, there's a couple kinds of uncertainty. One uncertainty is, will the tool give me an answer at all? And the other uncertainty, which is actually a really interesting one, is in the larger environment in which it runs, is it correct? So what we tend to do is we tend to take some code, we abstract it away from its larger environment, and then we find bugs, but then those bugs aren't reachable in the environment in which it's running. And that is it's a real challenge, right? Because you often involves a lot of interpersonal communication with the people who have trying to understand the environment in which people expect that the system is going to run. So yeah, I'm not sure if that answers your question, but that was my attempt.
Carl, microphone 26.
Carl Merrill, a member. Recently, there's been a lot of excitement about programs that are developed by DeepMind to play the game Go. And they use neural nets, and they develop their own rules. And I don't know that anybody knows how to analyze what those computers are actually developing. So how can you check whether or not they're working in a consistent manner, other than what they do in the outside world, perhaps?
That's an active research question, which is my way of saying I don't really know the answer. Yes, so the problem is undecidable, and we have developed heuristics which work when programs are written in a certain way. And there's a kind of an interesting thing I've learned over time. There are heuristics that I have used many times, which use the fact that a programmer on any line of a program never understands more than 20 things, right? And they can't, because if it were more complicated, they wouldn't be able to describe it to their colleagues or to their interns, and they wouldn't be able to get to lunch, right? So they have developed structuring principles such that at any line of the program, you never need to understand more than like 20 things or 30 things tops, but typically 5 or 3 things to understand why the program is correct. And we make use of that fact. And when you start having programs writing programs, which is what's going on in machine learning, all of those assumptions are broken, and thus my tools fall over. And I don't know of good work in the literature there's work in the literature, but I don't know of good work in the literature that's really solving this problem currently.
Microphone 25.
Stuart Reuter, member. Let me see if I can stretch you a bit. Most of us will be familiar with Asimov's laws of robotics. How would your tests, your techniques, work on those initial robots?
So I don't know Asimov's laws of robotics, so the answer will be easy, and I'll say I don't know.
Well, very simply, if I remember them right from my high school reading of science fiction, a robot may not harm a human by action. A robot may not harm a human by inaction, and only after those first two can the robot defend itself.
I see. Yeah. So those result in the sorts of properties that we'd prove, and that's a lot of people are doing that kind of thing. So there's Internet of Things, IoT. There's robotics, and then folks use these kinds of tools and express those types of properties exactly. So some of them are what we call liveness or safety. So safety is the program can't do bad things, and liveness is the program will eventually do something good. And you encode those in the temporal logic I showed you. You could encode those rules specific to the robot. So what you would see in the industry is consultants or members of staff at the manufacturer of the robot would do exactly that kind of work these days.
Jim, microphone 27.
James Griffin, I'm a member. Is it a fair inference to say from the remark that you just made about programs that write programs that if you tried to check for errors in a brain, then you'd be defeated.
You wouldn't want to use my techniques to reason about a brain because I would first need to cut your brain apart to get all the control flow graph in it. But a model of a brain, the techniques might work, well, let me say this. We switched gears in the talk, right? In the early days, I was talking about techniques for mathematical proof. And then I started talking about writing computer programs to find proofs. And the techniques for automatically finding proofs are probably not going to work to prove deep things about extremely detailed models of the brain. But if you have shallow models of some aspects of the brain, they probably would. If you want to prove really deep things about it, then you would probably need to do a manual deductive theorem proving, which then the limiting factor is the patience, intelligence, and the amount of time of the person doing that work.
Bob?
Bob Terry, a member. Harking back to normal inductive reasoning, you look at a sequence of things that won't stop. You can't enumerate them all, but you prove if K will work, K plus 1 will work. That seems like it could play a role here, but your standard problem has you just keeping enumerating and hoping that something will terminate. So can you put these two things together and ask of the system, do you know how to make yourself self-repairing so that you will terminate?
Yes. Let me get back to us. How much time do I have to answer this question? I don't like the look. I don't think I have long to answer that question. So let me. Okay. Here we are.
Take your time.
So your comment was very interesting because you highlighted this slide. So this you prove by induction. So this is a safety property because it's saying that all of the transitions in the program are a subset of all of the transitions allowed by this relation. And to do that, you're actually building a graph isomorphism or a relationship between the graphs, and you end up proving that by induction. So the tools find an inductive invariant. And the comment you made is that you can't prove termination by induction. And that's the really interesting part about this work is we turn the proving of termination into a sequence of inductive questions, right? So we're saying, does there exist an F such that by induction I can prove that the F holds? So so it turns out that termination cannot be proved by a single induction, but you can try and prove termination by looking for the right inductive proof, and you do that by search. And so that was the little algorithm I showed where we began trying to construct the termination argument. So then that was the presupposition of the question, and then the question was, can you synthesize repairs to programs? And that's an extremely active area of research. So yeah, so the program doesn't terminate. Can you find a precondition? And again, modern computer scientists have pulled out the old playbook from 1920, and they've discovered abduction and bi-abduction, and they're implementing techniques in logic that implement that kind of thing, and that's precisely what those tools do. So that's an interesting and active area of research.
James?
I have a question from the live stream from a viewer in Cedar Rapids, Iowa. Her name is Vicky. She asks, do you think that most artificially intelligent machines will work off intuition rather than brute force, such as DeepMind did? Is intuition in any way a danger as opposed to brute force?
Hello, Vicky. I don't know. So listen, I'm a simple man, right? I understand how to do proofs in mathematics. I know how to do logic, and I know how to write computer programs. And then I'm not involved terribly in philosophy and the ethics of computing. So I don't have an answer that would probably be useful. So I think I'm going to choose not to answer that question.
Are there limits to the size or complexity of the programs that you can try this technique on, or to the number of states that you could reasonably manage with a theorem prover like you're describing?
I can prove, there's a property that I can prove of basically any program of any size, and it's true. So it's content-free, right? It's essentially saying the program is a program. Yes, I can prove that, and the induction goes through extremely fast. And then there's a quite small, there's a little 5-line program. I wish I'd even written it down. It's easy to write down. There's a 4 or 5-line program that's fairly simple. It's actually expressible in linear arithmetic with while loops that no one knows if it terminates. And so it's called the Collat's program, or Collat's conjecture. It's a program that implements Collat's sequence. And if you could prove the termination of the sequence, there's a cash prize. So, so the size of the program definitely has an effect, but it's not the limiting factor. And I don't remember the precise numbers, but these days, so there's a bunch of important old proofs that are being proved now using mechanical theorem proving. So Kepler conjecture, the odd order theorem, 4-color theorem, et cetera. And you can read the papers about these techniques, and they encode in Cock theorem prover, Hall light, or et cetera, et cetera. And they have heuristics these days about how many lines of proof it'll take them a day. And they sort of understand now how to measure that. So they can take a proof in mathematics and grind through it, and they kind of know how long that's going to take. But in terms of lines of computer programs, definitely the larger, the harder. But I can't give you a precise answer.
James.
I have another question from the live stream. This comes from Addison from California. Addison asks, solutions to some more complex problems rely on approximations. Have you tested your tools on such problems? And is termination equally or more difficult to analyze or prove?
Okay, what was this person's name again?
Addison.
Addison from California.
Yes.
Thank you for watching my live stream. So how do you represent a very detailed program that's infinite state or unbounded state or a very large state space in a finite or very small amount of space? What you do is you actually abstract away and add non-determinism. So for example, when the condition says if x is less than y plus k, one thing you can do is you can say if non-deterministic choice. And so by doing that, you're adding extra executions into the program, you're adding extra paths through the text of the program. But if you can prove the correctness of that program where I've added executions, if you can prove the correctness of that program, the original, much more complicated program is correct. And that's really the magic trick of a lot of these tools. So we take large programs, we abstract them away by actually adding more bugs. We try and still prove the absence of bugs in that abstracted program. And if the abstracted program is correct, then the original program is correct. And we have techniques for automating that, and we have techniques for refining the abstraction if it loses too much information. Usually the first abstraction loses all information. There's way too many paths. The program is not correct. The rockets will not get launched. It's a bad program. And then we begin putting information back into the abstraction until we find one. And these approximations and these other complicating factors that programmers often find very hard to reason about actually fit in very well with these techniques. So we are in some sense adding approximation into the program. So I'm not saying it's free, but it's paid for in a sense by the techniques.
Tim?
I'm Timothy Thomas. I am a member of the society. My question is about sort of vague. I'm wondering, I feel from your talk like there's hope that my computer is not going to crash, my program is not going to fail, it's actually going to get better, your research is going to be valuable. But I'm wondering whether or not more complex programs come along and will always be behind this curve. And my children and grandchildren will live in the same frustration I live in. What do you think?
Only your grandchildren will know. So, I mean, in general, and I kind of alluded to that with some words in the slide, but I didn't really talk about this. In the early days, the fathers and mothers of, and by the way, there were many women in the early days of computing, were mathematicians, and they knew how to reason about programs. And it was very clear to them, and they could do it quite capably, right? So Turing proved correctness of programs. Many of the original algorithms were proved correct. But what happened is that features raced ahead. And this is kind of an interesting problem. Like, do I need to, boy, I'm going to go on long here. How long?
That's okay.
Okay.
You're fine. It's the last question.
You don't need to prove the correctness of the protocol you use to go get a quart of milk. You know, there's just certain things you don't need to prove. And so many features don't require proof. And what happened is that the computers, the technology, and the developers, and the delight, the cool wow factor, all the cool things you could do, raced ahead of the art and discipline of attempting to prove the correctness of programs, and it kind of got left, right? But now what's happening is that when personal safety, financial security, and so on ride on certain pieces of code, like the crypto, and the crypto is somewhat standardized, so a number of people are using it, there becomes enough reason that we would want to really pay attention to that code, that there are techniques, and I think that will continue to be so. And the more that the tooling becomes useful to programmers, the more that programmers will want to stay within the range of the tools for building critical pieces. So the games, your grocery delivery service probably will have bugs, and that's probably fine, right? But the crypto that encrypts your secret message needs to be correct. And the programmers who develop that are very interested in making sure the programs are correct. And what we've seen over time is that as the tools have gotten better, programmers are extremely interested in using the tools and extremely willing to change their programs to make sure the tools work for the programs that they're writing. And so I've had cryptographers entirely rewrite code so that the proof will go through. And so I think that there's a race between features and wow and delight, and computers are neat, and the safety and security of parts. And so we have to evaluate which parts do we depend on from a security perspective, from a physical security perspective, and make sure that those pieces are correct, and then the parts that aren't, we should just let computer programmers build cool stuff. So, thank you.
And thank you. Please join me in thanking Byron for a wonderful talk. And in recognition of your lecture tonight, please accept a copy of your lecture announcement signed by all the members of the General Committee. Thank you. Now, just a few closing announcements. First and foremost, thank you to all of our members, supporters, and sponsors. Without you, PSW simply could not continue. The Society depends on enthusiastic, active, and capable participants, so thank you for your support. If you are not a member, you can apply for membership on the Society's website, www.pswscience.org. Simply click on the blue membership tab on the left-hand side, and then that will take you to an application form that will ask for some basic information. Nothing difficult, no IQ tests, no obstacles to becoming a member. PSW membership is open to all people with a keen interest in science and PSW activities. If you have questions, please see Recording Secretary Heelan or any member of the General Committee after the meeting. PSW is a nonprofit educational organization exempt from taxation under Section 501c3 of the Internal Revenue Code. Dues and contributions are tax deductible. And if you have not yet paid your 2017-2018 dues, please see our Treasurer, John Ingersoll, after the meeting. Our next lecture is Friday, November 17th. The speaker will be Jerry Joyce of the Salk Institute and the Novartis Research Foundation. His lecture is entitled Life 2.0, Synthetic Self-Replicating and Evolvable Systems. On December 1st, we will welcome the physicist Nima Arkani Hamed of Princeton University. His lecture is entitled The Doom of Spacetime: Why It Must Dissolve into More Fundamental Structures. And then on December 15th, we will welcome David Smith of Duke University. His lecture is on metamaterials and is entitled Invisibility Cloaks and Other Impossible Optics, from Revolutionary Science to Disruptive Technology. The spring schedule is being completed and will be posted to the Society's website in due course. After the meeting is adjourned, please join us in the back of the room for refreshments and further conversation with the speaker. Our time in the Powell Auditorium ends at 10:30 p.m., after which PSW members and their guests meet at the Fairfax Hotel Lounge across the street for more conversation and discussion about the scientific topics of the day. If you wish to join us, please see Vice President Lloyd Mitchell or any member of the General Committee. Is there any further business of the Society? If not, I will now accept a motion from a member for adjournment. Second? All in favor say aye, all opposed say no. The 2,382nd meeting of the Society is adjourned.